Okay, so just now we learned about calculating the percentage of concentration in the alloy. One is in the mass percent and atom percent. The next one, if you're given a solid solution, the word means that the solid is in the solid phase. So when you deal with a material, you have a different phase of material. You can be in liquid phase, you can be in the solid phase, and you can have a liquid and solid phase. So the solid solution, they are in a single phase structure, single phase structure. So we start to go into defect or imperfection. So in a solid solution, normally you have substitutional and institution solution. By seeing on the screen here, substitutional means you replace the atoms of that element. You take out and then you replace. Or you inject a smaller radius of element to fill inside the space between the bigger element. Okay, so there are two types of solid solution that you have. Solid solution here is, it means solid solution here is that how do you dispense the element in atomic form? How do you put atom inside the structure? Either you replace it, you call it substitutional, or insertional. Right? Okay, so this is example of substitutional. Okay, substitutional here. This example is the so substitutional. Normally, we will choose this method by choosing the element that have the almost same radius, same size, almost same lah. You cannot get exactly the same, but almost same, right? Then let's see. Next, also very popular in your assessment. So we will follow one rules to define how many fraction of atom that can dissolve in other element in atomic percentage. Just now you learn mass percent and atomic percent. So we can do calculation on for the substitutional solid solution, means we replace atoms inside the solid solution by following these rules or HR rules, home rules. So the diameter is important. It cannot be more than 50%, or you can, in a layman term, means it should be very near to the host, very near to the original element. Because if you have a bigger diameter, you imagine this dark blue element. If it's bigger, when you push the bigger atom inside there, it will cause distortion in the crystal structure. All right, and also it will generate stress on the neighboring atoms. Right, and also you choose the same crystal structure. One is the size, the radius or the diameter, or another one you choose the same crystal structure. Means BCC, you choose BCC, then you can group them together. This is for the convenience of doing alloying. Means you want to mix two metal together to form alloy. You follow this one, then you're more easily to form that alloy that you want. If not, then you have to give more energy to force them to form. Okay. Okay. So crystal structure will deal with the solubility, means they're able to fit in each other. It's like having the same parking space. Third one is more on the electronegativity, means the element easily to give away electron or attract an electron. So the electronegativity should not be big difference, right? So if you want to mix, then in the periodic table, make sure it's at the same side of that element. Either you mix very near to the left-hand side or you mix very near to the right-hand side. You don't mix left-hand side and right-hand side, then very big electronegativity. Okay. If can, choose that the two elements have the same variance. So this same variance means same group. How you know it's same group? You follow the column. You pick the column. Right? So this is called home rules. When you do alloying, so these are the 4 factors that you need to consider when you do alloying. Okay. Any question on this one? Very important. Yeah, very important. This for one, very important. Maybe the question will not mention Holmes rules. It will ask you what factor that influence the solid solubility. You will see something that asks you to explain about solid solubility. So we are expecting you to explain these 4, or these 4 points is in your answer. Okay. Radius or diameter, crystal structure, electronegativity, and same variance. Okay. So normally this question will come along with this one, the percentage of calculation. Okay. We look at substitutional solid solution. Means you substitute the element inside the metals. So when you fall under solubility under substitutional method, then this 4 apply. What happens if you have another one? You call interstitial. Okay, again, you have 2 types of solid solution. One is true solid, one is true substitutional, one is called interstitial. Interstitial solution means they go into the space between the solvent or parent atom. What I show you just now, this is an enlarged diagram. It will go into the space between the atoms. So this is a schematic for iron and carbon alloy. You mix ferrum and C carbon. So the R for carbon is 0.07 nanometer. Iron is 1.2. Okay. So you will see that the carbon size is smaller than the iron. All right. So you see the dark color blue is a bit smaller compared to the neighboring atoms. The keyword for interstitial is the space. So this space or holes or voids is called interstices. Interstices. It's called holes. Right. Okay. And insert these holes or space available in a cubic crystal, they can classify as cubic site, which is surrounded by 8 neighbors for Cn of 8. Okay, Cn of 8. Okay, so this this one okay, there are 3 sites. There are 3 sites or 3 voids or space. One is called cubic. Second one is octahedral and tetrahedral. Octahedral, you get the Cn number is 6. Tetrahedral is 4. I'll give you a table or graph later. Okay, there are 3 type of site or 3 type of space for interstitial solution. There are 3 type of sites. So for interstitial, we always don't want to be so. This means if the neighboring atom should be bigger compared to the alien atom, right? So for example of interstitial, you look at the you look at the radius of the host, and then the solution or the way of meeting the alloying through interstitial method, you look for the R is below or less than the host R. Right? For this example, you look for the very small popular element, for example, hydrogen, carbon, nitrogen, oxygen. Okay. So this is just extra information. Important is the example, right? Okay, we look at example 3, then we stop. Okay, so example 3, it asks you to calculate the radius of the largest interstitial void or the space in FCC gamma ion. That is, the atomic radius of ion atom is 0.12 nanometer in FCC lattice, and the largest interstitial void or space occurred at this location. So it tells you that it occurred at half x 0, 0, 0, half y 0, and 0, 0, half z, and so on. Right? So this one fall under half family. Also identify the classification of the interstitial site. So we study a site in the 100 FCC lattice. So this is 100 lattice of the plane on the YZ plane. Okay. So we extend this plane in this form. So FCC is a face, right? So on this face, there is an atom in the center, and then 4 atoms here. 4 spheres at the side and 1 atom at the center. So that's what you see on the bottom right of the screen here. So you have 5 spheres, and then it pick one of the location, which is at the half 00 location. So it pick here, this is the origin, which is 0, 0, 0. Then we pick the first one, which is at here. It is half your, this is y, sorry, this is y. So you pick the second one, 0, half 0, the second one. This is half y. Then you put in the alien interstitial element there, solution there. Okay. So then you draw the parameter. You know that the crystal structure, this is all A side. So you have A from here to here, here to here. Then you know that the size of from here to here is A, but the radius, we use capital R for a big atom, capital R for big atom, small r for small atom, right? So one big sphere is equal to 2r, 2 small r, and then this is big R, big R. Okay. Then we need to find the relationship between the small r and the A. Derivation, you pick this rectangular, triangular, this 3 point, extend to the bottom center of the screen. Still, we are seeing Z and negative Y. The axis is negative Y because it's not negative. Let's say we take Y, this Y. So important is the length of that particular location. So here to here, this is R and this is R. So here is 2R. Then this is half of the lattice, half of the cell. So you have half A. This is half A. Then here to here is half A. Here to here is half A. Okay, then we start to do derivation. So first linear equation, 2r, r plus 2 small r, capital R, you have 2r plus 2r, 2 small r equal to A. Agree? Makes sense, right? Then to calculate the r, you have a rectangular, triangular here. You do trigonometry calculation. This one square equal to this side square, this side square. Trigonometry. Right? You rearrange, you'll get half A square. You solve for R term. You put this one over here, you get 1 over square root of 2A. The purple color one is on for the triangular on the bottom here. Okay, so you have 3 equations there. And you rewrite what is A. A equal to 2 square root 2R. Okay, you have 2 equations there. Then you substitute back. You substitute back, so the total equation here, you will get 2R plus 2 capital R plus 2 small r equal to 2 square root 2R. Okay, so you get the R here, this R, this small r, or the small radius for the interstitial alien atom that you want to put inside there. Because this is the space that you have. This is the maximum space that you can park. You want to find the space that you're able to park inside there. So that's why all the calculation you find is to find the R. You want to find what is the maximum space, maximum radius that you can park inside there. So from all the calculation on the screen, at the end you find the R, the small r is 40% of your big capital R. Means that the element that you can put in is 40% of the neighboring sphere. Right? 41.4%. Okay. So the R, the host R given here is 0.129, the ion atom here. So you substitute the space that you can. Then the R that you can fit in is 0.534 nanometer. This is the maximum size that you can park inside the interstitial void here or space here. Okay. Any size bigger than this one is no longer, it will create stress to the neighboring and it's not a good alloying item. It's not a good interstitial solution. Okay, this is just additional information that I illustrate in a three-dimensional form. So the given interstitial void have four neighbor in the plane. So if you imagine you are the green color dot, you have four neighbor, right, around you. And then you have another two at the top and bottom. Okay, so you have six neighbor. This is how you calculate the CN number. You have six CN number for the interstitial or the green color dot on the screen there. Okay, this is called coordinate number 6. Okay, makes sense to you? Why you get 6? Yeah. So because of this CN number 6, the interstitial void is octahedral void. This one by this statement that we learned. This side is important because by knowing your CN number, if you get CN number 8, it is fall under cubic side. If it's under tetrahedral, if your CN is 6, then it's under octahedral. If your CN number is 4, then it's under tetrahedral. Just now, the tutorial question just now is 6, so it's fall under tetrahedral side. Okay. Then, any question for example 3? Any? All right. So for FCC, normally we solve in this procedure. We pick a plane, then we draw the plane on that one. Again, you can see that FCC will always pick one of the phase to do analysis. But for BCC, we always chop at the center to do analysis. We always chop at this plane to do analysis. Okay. Yeah. So it depends on the crystal structure. Okay. Okay. So we stop here. Okay. Next lecture we go into imperfection of what you have.